Good morning, all of you. Welcome to Sri Jayendra Bank Zone. So, in the last lecture, we have discussed about Vesper theory as well as valence bond theory. And now, just hybridization we have just started. In this class, we will discuss more about hybridization and types of hybridization. So, what is hybridization? Let us recap now. So, hybridization is nothing but the intermixing of atomic orbitals, the intermixing of atomic orbitals to form new equivalent orbitals of almost same energy, to form new equivalent orbitals of almost same energy, and this is nothing but hybridization. And we have different types of hybridization. So first we'll discuss what is sp hybridization. So as I already mentioned in the last class, how many types of hybridization we have. So now we are discussing total about all the hybridizations and how to find hybridization also we are going to discuss now. So let us start the class now. So what is sp hybridization? sp hybridization takes place by mixing. It takes place by mixing one s orbital and one p orbital. So when one s orbital overlap with one p orbital to form a new equivalent orbital called sp orbital, so it is called sp hybridization to form. So to form two new equivalent orbitals. So when one s orbital and one p orbital to form. So when one s orbital overlaps with when one s orbital and one p orbital to form two equivalent sp hybrid orbitals. Each sp hybrid orbital contains 50% s character. This is important for objective. So in s orbital and sp hybridization, it has 50% s character and 50% p character, and the two orbitals are directed in opposite direction, and hence the geometry of the molecule will be linear. Again, writing here clearly. So the two hybrid orbitals The two orbitals are directed in opposite direction, and hence the geometry of the molecule will be linear. So by the means of sp hybridization, we can take the shape of the molecule also. So what is sp hybridization? When one s orbital overlaps with one p orbital, resulting in the formation of two new equivalent orbitals. So two equivalent orbitals. Equivalent means of almost same energy. Equivalent means what? Same energy. This is called equivalent orbitals, and it has 50% s character and 50% p character. Example BeCl2, beryllium chloride. So if you see the ground state configuration of beryllium is 1s to 2s2, and in the excited state, one of the 2s electron excited is a 2s electron is excited to 2p orbital. So then it becomes 1s1, 1s2, 2s1, 2p, 2p2, 1s1, 1s2, 2s1, 2p1, 2s1. One electron from s orbital jumps to p orbital, which resulting in the formation of 2s, 2p overlapping, 2s, 2p overlapping. These two orbitals undergo sp hybridization to form two hybrid orbitals. These hybrid orbitals overlap with 3p orbitals of two chlorine atoms, because chlorine is 1s to 2s to 2p6, 3s to 3p5. So it overlaps with 3p orbitals of two chlorine atoms to form two BeCl sigma bonds. The shape of the molecule is linear and the bond angle is 180 degrees. I hope it is clear. So this is called formation of beryllium chloride. So in the ground state, electron configuration of beryllium is 1s to 2s2. And when you give some energy to this ground state beryllium atom, the electron from 2s electron excited to 2p orbital. So 1s to 2s1, 2p1. So this two orbitals, that is s and p orbitals, overlap with each other, and they form two vacant sites beryllium atom they form two vacant sites, and these two vacant sites are occupied by two chlorines, and hence the formation of BeCl2 takes place, and the shape is linear. So the shape is what? Linear, and it is nothing but a bond angle is 180 degrees. I hope it is clear. So sp hybridization is a type of hybridization in which one s orbital overlaps with one p orbital, resulting in the formation of two equivalent orbitals. Two equivalent orbitals means, yeah, equivalent means what? Of almost same energy. And these two equivalent orbitals will be overlap with 3p orbitals of two chlorine atoms. 3p orbitals of two chlorine. How why it is overlapping with 3p orbitals? Because chlorine configuration, chlorine atomic number 17. So its configuration is 1s2, 2s2, 2p6, 3s2, 3p5. So the valence configuration is 3p5. So out of which only two chlorines will combine with two berylliums and forms BeCl2. So, so the two equivalent orbitals so formed by the hybridization by the overlapping of s and p orbitals of beryllium will overlap with 3p orbitals of two chlorine atoms to form two BeCl sigma bonds, and hence the shape is linear and the bond angle is 180 degrees. I hope it is clear. This is called sp hybridization. In sp hybridization, s character is 50% and p character is 50%. Next, so one more example here. They are being given linear beryllium. So s orbital overlaps with one p orbital. One s orbital overlaps with one p orbital, resulting in the formation of linear sp2 hybridized, and the shape will be like this. Example, one more example is stellene. Stellene, the configuration of carbon is 1s2, 2s2, 2p2. So one electron from s orbital overlaps with 3p orbitals. Actually, sorry. Here, in the excited state configuration, one electron from the s orbital goes to p orbital. Then, so 2s, one electron, sp3. sp, we have three orbitals, and 2p, 2pxy, 2py1. So due to this, what happens? They undergo overlapping. One s orbital and one 2p orbital undergo mixing to form two sp hybrid orbitals. These hybrid orbitals overlap with each other and also with one s orbital of two hydrogen atoms to form two CH and two 1 sigma sigma bond. So it forms two CH bonds and one CC sigma bonds, and which the shape is linear. So each carbon atom is now left with two unhybridized orbitals, 2p orbitals with one unpaired electrons. These 2p orbitals overlap laterally to form two pi bonds. Hence, the carbon atoms are bonded by a triple bond in a stellene molecule. The bond angle is shape is linear and bond angle is 180 degrees, but overlapping is different in this case. What happens here? Sideways overlapping and unhybridized 2p orbitals also takes place. This is called sideways overlapping of unhybridized 2p orbitals, which results in the formation of, so how many sigma bonds, how many pi bonds in the last session we have discussed. So from this also we'll get the same. So in a stellene molecule, it has C triple bond C and one hydrogen here. So it has how many sigma bonds? One, two, three sigma bonds. Three sigma bonds and two pi bonds. So it has three sigma bonds and two pi bonds. So this is the structure of stellene. I hope it is clear now. Next. So sigma bond, that is end-to-end overlapping, and pi bond, sidewise overlapping. Sidewise overlapping is sigma bond. End-to-end overlapping is, sorry, sideways overlapping is pi bond, and end-to-end overlapping is sigma bond. So it has two sigma bonds and two pi bonds. Total in between sigma, before forming pi bond, it should form sigma bond also. So this is called sigma pi bond formation in middle. These are nothing but pi bond formations, and here sigma bond, sigma bond. I hope it is clear. Next, second type of hybridization. This type of hybridization is due to intermixing of one s orbital and two p orbitals. How many orbitals? Two p orbitals. One s orbital. When one s orbital overlaps with two p orbitals, resulting in the formation of three new equivalent orbitals. Three new equivalent orbitals. You can see here I'm writing. So three new equivalent orbitals. Equivalent means same energy. The three sp2 hybrid orbitals are directed. The three sp2 hybrid orbitals. The three sp2 hybrid orbitals are directed along three corners of a triangle. They are directed towards the three corners of a triangle. Hence, the shape of the molecule will be trigonal planar with a bond angle of 120 degrees. The difference between valence shell electron pair repulsion theory and hybridization is this. In hybridization, the overlapping of orbitals takes place. That is due to the formation of sigma bond and pi bond. And this sigma bond, pi bond concept, where we got? We got it from valence bond theory. We got it from where? Valence bond theory. So What is sp2 hybridization on the whole? This type of hybridization is due to intermixing. I use this word several times. What is hybridization? Means intermixing of atomic orbitals. General definition: intermixing of atomic orbitals. So here, intermixing of one s orbital and two p orbitals. So which results in the formation of three new equivalent orbitals. The three sp2 hybrid orbitals are directed along three corners of a triangle. Hence, the shape of the molecule is trigonal planar with a bond angle of 120 degrees. Let us take the example of BCl3. The ground state configuration of BCl3 is boron is 1s2, 2s2, 2p1, and the exit state of configuration of boron is 1s orbital. One electron from s orbital jumps into p orbital. So, due to which what happens? It forms 1s2, 2s1, 2p2, 1s2, 1s2, 2s1, 2p2. So, 1s orbital, two p orbitals. That's all. Simple. Just if you have to take the central atom configuration, that is more than enough. What type of hybridization it can form, we can easily estimate. So here, one electron from s orbital jumps into p orbital, due to which what happens? The incomplete orbitals will be 2s1 and 2p2. So one s orbital overlaps with two p orbitals, resulting in the formation of sp2 hybridization. And in this hybridization, like this, we have 2s orbital, 1 and 2p orbitals. Electrons will present. 2s and orbital and 2p orbitals undergo mixing to form three sp2 hybrid orbitals. These hybrid orbitals overlap with 3p orbitals of three chlorine atoms. Three chlorine atoms, 3p again. Here, chlorine already we know 3p, to form three BCl sigma bonds. Thus, BCl3 molecule has trigonal planar shape with a bond angle equal to 120 degrees. So this is called trigonal shape, trigonal planar shape. So this is trigonal planar shape, forming of three sigma bond, 1 sigma, 2 sigma, and 3 sigma with three chlorine bonds. And this is as they are forming end to end. Here, very important, you can see here, this is nothing but what? Nothing but what? End to end. End to end overlapping. Whenever there is end to end overlapping, it leads to the formation of sigma bond. Sigma bond. So here 1 sigma, 2 sigma, and 3 sigma. So on the whole, it forms 3 sigma bonds and BCl3. And in sp2 hybridization, S character will be equal. So it is two P characters and S. So it has 30% S character and 70% P character. So 30% S character, 70% P character. I hope it is clear now. Next, the ground state electron configuration of carbon. One more example here we are suggesting. It is 1s2, 2s2, p2, and excited state one electron from s orbital jumps into p orbital, which results in the formation of 1s2, 2s1, 2p3. So it is going from 1s2, 2s1, 2p3, which now we'll see here. What happens here? The formation of ethene or ethylene, both are same. So 2s orbital, how many? 1 and 2p, 3. And sp2, 2pz. sp2 and 2pz. Here, if you understand, in BCl3, it is very simple. So overlapping takes place. But here, 2s orbitals, 2p orbitals, and 1s orbital, 3p orbitals. But it is not forming, it is not overlapping like this. It forms differently because due to the formation of pi bonds. 1s orbital and 2p orbitals undergo mixing. 1s orbital and 2p orbitals. This they'll ask in the objective point of view. How many s orbitals, how many p orbitals? One s orbital and two p orbitals undergo mixing to form two sp2 hybrid orbitals. These hybrid orbitals overlap with each other and also with one s orbital of four hydrogen atoms to form four CH sigma and one CC sigma bonds. So, how many sigma bonds and how many pi bonds? Let us see now. Now we are discussing about formation of ethene. Ethene is C2H4. How much it is? C2H4. Ethene is C2H4. C double bond C, H, H, and one more H here, one more H here. So for each carbon, just we can write the H over here. Here also the same thing. So for each carbon, two hydrogens, and these two carbons are linked with double covalent bond. Whenever double covalent bond is there, pi bond is formed, and four sigma bonds. And here it is nothing but how many sigma bonds? 1, 2, 3, 4 sigma bonds with four hydrogen atoms, and one pi bond, one sigma with two carbon atoms. On the whole, it is how many sigma bonds, how many pi bonds? You can see here four CH bonds and one CC sigma bond. So here total 4 sigma bonds plus 1, total 5 sigma bonds and 1 pi bond. So number of sigma bonds and pi bonds in ethene is, number of sigma bonds and pi bonds in ethene is 5 sigma 1 pi bond. I hope it is clear. So this is called formation of ethene molecule. So it is C2H4. So 1, 2, 3, 4 sigma bonds and 1 pi bond. And in 1 pi bond, in double bond, we have 1 sigma bond as well as 1 pi bond. So that is clearly shown in this picture very neatly. And here it is nothing but sigma bonds. Why it is sigma bonds? Because end-to-end overlapping. It is what? End-to-end overlapping. And this is pi bond and this is sigma bond. Pi bond is sidewise overlapping. This is called sidewise overlapping. Sidewise overlapping, end-to-end overlapping. I hope it is clear. Next. Each carbon is left with one unhybridized pz orbital. These orbital overlaps laterally to form a pi bond. So these two orbitals overlap to form pi bond. Hence, the two carbon atoms in ethylene molecule are bonded by double bond, and the bond angle of HCH is 120 degrees, and the orbital overlap and the structure of ethane is as shown in the diagram. Next, we have sp3 hybridization. Very, very important. sp3 hybridization. So, what is sp3 hybridization? In this type of hybridization, one s orbital and three p orbitals undergo mixing with each other, intermixing with each other to form four sp3 hybrid orbitals. How many sp3 hybrid orbitals? Four. And here, sorry. So it is four sp3 hybrid orbitals. In sp3 hybrid orbitals, 25% s character and 75% p character. How many? 25% S character and 75% P character. So it has 25% S character, 75% P character, and they form four new equivalent orbitals. So how many orbitals? Four new equivalent orbitals. Equivalent means same energy. Again, I'm repeating the same word. Equivalent means same energy. So in this case, this is called sp3 hybridization. One S orbital overlaps with three p orbitals. Example, these hybrid orbitals are directed towards four corners of a regular tetrahedron. So regular tetrahedron. Thus, the molecule will have a tetrahedral shape with a bond angle of 109.5 degrees. So now we have sp hybridization, linear shape, sp2 hybridization, trigonal planar shape, and sp3 hybridization, tetrahedral shape with bond angle of 109.5 degrees. Let us consider methane. The ground state configuration of carbon is 1s2, 2s2, 2p2. And for this carbon, if you give some energy, it goes to excited state. And this excited state configuration of carbon is one electron from s orbital goes to p orbital, which results in the formation of 1s2, 2s1, 2p3. So 1s2, 2s1, 2p3. Then this forms. So 1 2s orbital overlaps with 3p orbitals. 1 2s orbital overlap with 3 2p orbitals, which results in the formation of sp3 hybridization. One s orbital and three 2p orbitals. One s orbital and three 2p orbitals undergo mixing to form four sp3 hybrid orbitals. These hybrid orbitals overlap with one s orbitals to form four hydrogen atoms to form four CH sigma bonds. These sigma bonds are directed towards four corners of a regular tetrahedron. Regular tetrahedron. Shape is tetrahedron. Thus, methane has tetrahedral shape with CH bonds, with HCH bonds angle 109.5 degrees. The orbital overlap and structure of methane is as shown in the diagram. You can see the diagram now. sp3 hybridized carbon plus 4 H orbitals, 4 1s orbitals. So 1s orbital, H will have what type of orbitals? S orbital. And P will have, so overlapping resulting in the formation of four sigma bonds. How many sigma bonds? Four sigma bonds. End-to-end overlapping only. End-to-end overlapping. Here, this is s orbital, p orbital of carbon. S orbital of hydrogen, p orbital of carbon. S orbital of hydrogen, p orbital of carbon. S orbital of hydrogen, p orbital of carbon. So they overlap end-to-end. As they are overlapping end-to-end, it results in the formation of how many sigma bonds? So it results in the formation of four sigma bonds. How many sigma bonds? Four sigma bonds. The structure will be C H H H H. And one more important thing I want to tell you. All alkanes, all alkanes, that is ethane, methane, propane, alkanes means saturated hydrocarbons, alkanes, undergoes sp3 hybridization. And all alkenes undergoes, this point is important, please note down in your book. Alkenes undergoes sp2 hybridization and alkynes undergoes sp hybridization. So what are alkanes, alkenes and alkynes? Already you know. Alkenes and alkynes together they are called as unsaturated hydrocarbons, whereas alkenes are nothing but double bonded carbon atoms. So these are called unsaturated hydrocarbons. And unsaturated hydrocarbons either undergo sp2 if it is an alkene or sp if it is an alkyne. So if triple bond is there, alkyne, and double bond is there, alkene, and single bond is there, alkane. So single bonded carbon atoms will undergo sp3 hybridization, and alkenes undergo sp2, and alkanes undergo sp hybridization. I hope it is clear. Just note down this, very important. All alkanes undergo sp3 hybridization, alkenes undergoes sp2 hybridization, and alkynes undergo sp hybridization. Why I am discussing this? Because they will ask in the examination what is the hybridization and shape. So next example is ammonia. The ground state configuration of nitrogen is 1s2, 2s2, 2p3. 1s2, 2s2, 2p3. So what is the bond angle in methane? 109.5 degrees. Whereas here, when you go for excited state, 1s orbital in nitrogen goes to p orbital, then it becomes, these orbitals undergoes sp3 hybridization to form four hybrid orbitals. The three hybrid orbitals with unpaired electron will overlap with 1s orbital of three hydrogen atoms. See here. Nitrogen has what orbitals? We have nitrogen has three p orbitals. How many three p orbitals? So the three hybrid orbitals with unpaired electron of nitrogen will overlap with oneness of orbital of three hydrogen atoms to form three NH sigma bonds. But the fourth hybrid orbital, which is fully filled with two electrons, will remain as a lone pair of electrons. Here, lone pair is important on nitrogen due to the presence of lone pair of electrons. As we already discussed in Vesper theory, the nitrogen, the shape of the molecule appears as pyramidal, not tetrahedral. Even though, so this question they'll ask in the examination, even though ammonia undergoes sp3 hybridization, but its bond angle, but its shape is not tetrahedral. Why? Because of the presence of lone pair of electrons. What is the reason? Due to the, here I'm writing here, please note down, due to the presence of, due to the presence of lone pair of electrons, lone pair of electrons, ammonia undergoes pyramidal shape. I hope it is clear. Due to the presence of lone pair of electrons, ammonia undergoes pyramidal shape but not tetrahedral, and bond angle is also slightly reduced to 107 degrees due to higher repulsion of lone pair bond pair of electrons. I hope it is clear. So why, even though ammonia undergoes sp3 hybridization, but the shape is not tetrahedral due to the presence of lone pair of electrons on nitrogen atom in the ammonia, the shape of the molecule is pyramidal, not tetrahedral, because lone pair occupies more shape, as lone pair occupies what is this, space. Since lone pair is occupying more space, so it will not have regular geometry, it will have distorted geometry, as we discussed in the case of Vesper theory. So that distorted geometry is nothing but due to lone pair, and the shape of ammonia is expected to be tetrahedral, but the shape is, actual shape is pyramidal. That is due to the presence of lone pair of electrons. So this line is very important. You can underline this line, due to the presence of lone pair of electrons on nitrogen atom. The shape of the molecule appears as pyramidal shape. So these 2 points are important. And bond angle is 107 degrees. Next we have same case water also. Water also have undergoing sp hybridization, and water also undergoes sp3 hybridization, and but the shape is not tetrahedral. Let us see that also. So the orbital overlap diagram and structure of ammonia will be like this. And this is called lone pair of electrons. This is called what? Lone pair. They are not involved in bonding. This is bond pair, this is bond pair, and this is bond pair. So one s orbital of hydrogen combines with p orbital of nitrogen. Combines with p orbitals. So three p orbitals of nitrogen to form four new equivalent orbitals, and that fourth orbital is empty. So due to which what happens? The shape is not tetrahedron. The shape is only pyramidal shape. I hope it is clear. Next, if you, I just now as I told you, let us see water. The ground state configuration of oxygen is 1s to 2s to 2p4, and the excited state. So ground state, if we take into consideration, 1s to 2s to 2p4. So 2s to 2p4. So in p orbitals we have 4 electrons, and s orbital we have 2 electrons, and sp3 hybridization 1s and 3p orbitals overlap with each other and form sp3. So water also undergoes sp3 hybridization. How can you detect sp3, sp2, sp hybridization? That also I'll tell you. One formula is there. Nothing, it is nothing but based on n factor. Here itself I will explain you. So if you know the n factor, so in water molecule, how many bond pairs? Oxygen, it has two lone pairs and two bond pairs, and these two bond pairs with two hydrogens. So how many total? So n factor is two bond pairs and two lone pairs. So two bond pairs, two lone pairs means total it is equal to 4. So 4 means n factor is equal to 4 means sp3 hybrid orbitals, sp3 hybridization, sp3 hybridization. So water also undergoes sp3 hybridization, but its shape is not tetrahedral because due to the presence of lone pair of electrons on oxygen atom, due to the presence of lone pairs, this is lone pair. So due to the presence of lone pair of electrons on oxygen atom, it has a bent shape, that is an angular shape. I hope it is clear. So angular shape. Water will take what type of shape? Angular shape. So these hybrid orbitals undergo sp3 hybridization to form four hybrid orbitals. Two hybrid orbitals having unpaired electron will overlap with one s orbital of two hydrogen atoms. As I told you, four hybrid orbitals it also will form, but only two will be filled up by two hydrogen atoms, and remaining two oxygen OH sigma bonds, and the remaining two hybrid orbitals are fulfilled and they remain as lone pair of electrons. See, the remaining two hybrid orbitals are fulfilled and they will remain as lone pair of electrons. So the water molecule has a bent shape due to the presence of two lone pair of electrons. That's why its shape is angular or bent shape. Both are same. We can call it as angular shape or bent shape. So we can write for water. We can you also please note down. So we can write bent shape as well as angular shape. So the shape of water is angular or bent shape, and even the bond angle is also 104.5 degrees, or we can say 105 degrees. 104.5 degrees, or you can say 105 degrees. I hope it is clear. Let us see the shape of water molecule. The bond angle is reduced from normal tetrahedral angle, that is 109.5 degrees to 104.5 degrees due to lone pair repulsions, which is higher than that of lone pair bond pair as well as bond pair repulsions. So the structure of orbital overlapping in water is as shown in the diagram. There is a beautiful picture is being shown to you. It has two lone pairs, non-bonding electron pairs, and two bonding electron pairs, due to which its shape is angular, not tetrahedron. Shape is what? Bent shape, not tetrahedron. I hope it is clear. Now I'm sharing the new topic in this. I'm sharing it again. Yes, please note down. Continue the topic of hybridization. So more about hybridization we'll discuss now. Different types of hybridization we're going to discuss now. Let us see now. So I'm not yes. So hybridization of elements having d orbitals. So what are the elements we are having d orbitals? Let us see now. So the elements of third period have 3D orbitals. Already we know the third period elements will have 3D orbitals. 3D orbitals. The energy of 3s, 3p, and 3D orbitals are comparable. 3s, 3p, because they have the same principal quantum number and comparable, and also the energy of 3D orbitals also is comparable with 4s and 4p orbitals. Thus, the hybridization involving 3s, 3p, 3d, 3d, 4s, and 4p orbitals are possible. So, the important types of hybridization involving d orbitals are sp3d, dsp2, sp3d2, sp3d3. These are the different types of hybridations we are going to discuss now. So, total we have, so far we discussed three hybridations. What are those? sp, sp2, and sp3. Now we will discuss more about hybridations involving d orbitals. So, formation of PC alpha sp3d hybridation. sp3d hybridation. The ground state configuration, outermost configuration of phosphorus is 3s2 3p3 and 3s to 3p3. Excited state, what happens? It one s orbital electron in electron in s orbital goes to d orbital because it has empty 3d orbitals, because 3s, 3p, 3d are comparable energies. So it has empty d orbital. So one electron will go from s orbital to d orbital, which results in the formation of 3s1, 3p3, 3d1. So one s orbital overlaps with 3p and one d orbitals, resulting in the formation of sp3d. sp3d means 1 plus 3, 4, 4 plus 1, 5. So they are going to form how many equivalent orbitals? Five new equivalent orbitals. How many? Five. Five new equivalent orbitals. And these five new equivalent means of almost same energy. These are called hybrid orbitals. Five new equivalent hybrid orbitals. And these five new equivalent hybrid orbitals combined with five new equivalent hybrid orbitals combines with five chlorines of p orbitals of chlorines and forms PCl5. It forms what? PCl5 and PCl5. So all are, it takes the shape trigonal bipyramidal. Trigonal bipyramidal, as we discussed in Vespati. Shapes are not will not change, but hybridization explanation is different. So one 3s, one 3p, and one 3d orbitals undergo hybridization to form five hybrid orbitals of equivalent energy. These five hybrid orbitals are directed towards the corners of trigonal bipyramidal as shown in the diagram. The diagram will be showing in the next slide. So the in PCl5, all bond angles are not equal to each other. Three of the Cl bonds at an angle of 120 degrees and are directed at the corners of triangle. And these bonds are known as equatorial bonds. So what are these called? So this matter is very, very important. They'll ask in the exam which are the following is true regarding PCl5. In PCl5, all bond angles are not equal to each other. Three of the for PCl bonds at an angle of 120 degrees and directed towards the corners of the triangle. And these bonds are known as what bonds? They are called as equatorial bonds, means they are equidistant from each other. And the three two PCl bonds are perpendicular to the equatorial bonds, and these bonds are known as axial bonds. So in PCl5, we have three equatorial bonds and two axial bonds. Very, very important. And equatorial bonds will be perpendicular to the axial bonds. Our axial bonds is perpendicular to the equatorial bonds. I hope it is clear. So this matter is very, very important for objective point of view. And due to this, what happens? They form a shape that is called the axial bond pair of electrons will experience more repulsion from the equatorial bond pairs, and hence the axial bonds are slightly longer and weaker than the equatorial bonds. Due to this, PCl is more reactive in nature. So the axial bond pair of electrons will experience more repulsion. What are those which are away from the equatorial bond pairs, and hence the axial bonds are slightly longer, and these are two. So equatorial same and axial bonds. So this is the trigonal bipyramidal structure of PCl5. I hope it is clear. So then the equatorial bonds, due to this PCl5 is more reactive in nature. I hope it is clear. Next. Formation of SF6 molecule. The ground state configuration of sulfur is next example sp3d2 hybridization. What is this? sp3d2 hybridization. Moving it slightly. So sp3d2 hybridization. So the ground state configuration of electron configuration of sulfur is 3s2 3p4. So it has one 3d orbital. So empty 3d orbital. One s electron goes to 3d orbital which results in the formation of 1s, 3p, and 2d. 1s, 3p, and 2d. Total it is nothing but equal to how much? This they are forming six new equivalent orbitals. Six new hybrid orbitals. You can say simply equivalent orbitals are hybrid orbitals. So these six hybrid orbitals combines with six fluorines, and forms sp3d2 hybridation. One s orbital over with 3p and 2d orbitals to form six new hybrid orbitals, and they form sp3d2 hybrid orbitals. sp3d2 hybridation. I hope it is clear. Next. So one 3s, 3p, and 2d are hybridized to form six sp3d2 hybridized orbitals. These orbitals overlap with 2p orbitals of six fluorine atoms. 2p orbitals of six fluorine atoms, because fluorine configuration is 1s2, 2s2, 2p, 5. So 2p 5 means definitely the outermost configuration is 2p. So 2p orbitals of six fluorine atoms to form six sf sigma bonds. These bonds are directed towards corner of a regular octahedron, and the bond angles of SF6 are equal to 90 degrees. And the structure of SF6 is octahedral. This is called octahedral structure. I hope it is clear. Next, summary of hybridization you can see here. Number of electron pairs, 2 bond pairs, sp hybridization. 3 low bond pairs, sp2 hybridization. 4 bond pairs, sp3. 3 bond pairs, 1 lone pair, sp3. Shape is pyramidal. Two bond pairs, two lone pairs, sp3, but shape is bent. Example, water. And five bond pairs, sp3d. Six bond pairs, sp3d2, octahedron. So this is the summary of hybridization. Now limitations of valence bond theory. Valence bond theory successfully explains bonding in most of the covalent molecules. According to VBT, the oxygen molecule do not have unpaired electrons and expected to show a diamagnetic behavior, but oxygen is observed to be paramagnetic. Very, very important. So oxygen is not diamagnetic, it is paramagnetic. According to VPT, the oxygen molecule do not have unpaired electrons and the expected to show a diamagnetic behavior. So in order to explain such limitations of VPT, one more theory is proposed by Mulliken and Hunt, known as MOT, that is molecular orbital theory, that we are going to discuss now. According to molecular orbital theory, the atomic orbitals combine to form new set of orbitals known as molecular orbital. So two atoms combines to form molecule. Generally equation we know. But here two atomic orbitals combines to form molecular orbital. A molecular orbital is a three-dimensional region in space around all the nuclei of atoms of the molecule where there is maximum probability of finding an electron. So what is a molecular orbital? It's a three-dimensional region in space around all the nuclei of atoms of the molecule where there is probability, maximum probability of finding an electron. So the silent features of MOT are the atomic orbitals of all the atoms of a molecule combine to form molecular orbitals. The electrons present in the molecular orbital will belong to the molecule as a whole and not concentrated on any particular atom. That is, the molecular orbitals are polycentric in nature. Very important here. The molecular orbitals are polycentric. Polycentric means they have multiple centers. So which of the following is true regarding molecular orbitals? The atomic orbitals of all the atoms of a molecule combine to form molecular orbitals, just like atoms combine to form molecules. The electrons present in the molecular orbital will belong to the molecule as a whole and not concentrated on any particular atom. So the molecular orbitals are polycentric in nature. I hope it is clear now. So the number of molecular orbitals formed is equal to the number of atomic orbitals combined. Half the molecular orbitals are known as bonding molecular orbitals, and the other half of the molecular orbitals are known as anti-bonding molecular orbitals. So we have bonding as well as anti-bonding. The energy of bonding molecular orbitals is less than anti-bonding molecular orbitals, and the electrons in bonding molecular orbitals BMO favors bond formation, and the electrons present in ABMO anti-bonding molecular orbitals do not favor bond formation. So very important here. Some favors bond formation, some do not favor bond formation, due to which only we have defined. So the filling of molecular orbitals of different energy will follow Hansul Avo principle and Pauli's exclusion principle. So Hansul, Ahu principle, and Pauli's exclusion principle we already know. So based on these rules only, they'll fill up the electrons in the molecular. Now, formation of linear combination of atomic orbitals, LCAO method. According to quantum mechanics, the atomic orbitals are represented by a wave function psi, which represents the amplitude of the wave function of the electrons. So what is psi representing? This psi we have seen in Schrodinger wave equation, the last session. So what is psi represents? Represents the amplitude of the wave motion of the electrons. When the atomic orbitals combine to form molecular orbitals, these wave functions are added or subtracted. This is an approximate method to explain the formation of molecular orbitals. When the wave functions are added, the molecular orbital formed is BMO, bonding molecular orbital, and the wave functions are subtracted. The molecular orbital is formed is ABMO, that is anti-bonding molecular orbital. So when the wave functions are added, if you are psi, the molecular orbital formed is called BMO, and the wave functions are subtracted. The molecular orbital formed is called as ABMO, that is anti-bonding molecular orbital. Continuation. BMO is obtained by the constructive overlapping of atomic orbitals, and the ABMO is obtained by the destructive overlapping of atomic orbitals. So constructing overlapping is bonding molecular orbital. Destructive overlapping is anti-bonding molecular orbitals. Example, let us see. Let us consider the two wave functions of two hydrogen atoms A and B as psi of A and psi of B. This is called psi of A and psi of B. These two orbitals undergoes constructive and destructive overlapping to form bonding molecular orbital as well as anti-bonding molecular orbital. This can be represented as for psi of BMO, bonding orbital molecular. So bonding molecular orbital, we know already we have to add of the wave function. We have to add the wave functions of two hydrogen atoms, that is psi of A plus psi of B. And for getting anti-bonding molecular orbitals, we should subtract, that is psi of A minus psi of B. These two molecular orbitals are represented as sigma 1s, sigma star 1s. Let us see simple example, I'll tell you. So bonding orbital sigma 1s and sigma star 1s. Sigma 1s is called bonding orbital. Sigma star 1s is called anti-bonding. So this is called bonding molecular orbital, and this is called anti-bonding molecular orbital, ABMO. So sigma star represents then anti-bonding. How will you get? By subtracting the wave functions of the two hydrogen atoms, and by adding the wave functions of two hydrogen atoms, we are getting bonding molecular orbitals. So these two molecular orbitals are represented as sigma 1s and sigma star 1s. Whenever you get pi 1, pi 1s, pi 2s, like that, pi also will get. So what we are going to discuss in that, we'll discuss later. Next, sigma 1s molecular orbital will have lesser energy than sigma star 1s orbital. This can be represented as, you can see here, energy bonding energy diagram. Sigma 1s, 2 electrons. Sigma star 1s, no electrons in hydrogen molecule. So it is kept empty. And one will be, these two are bonding. Bonding means upward arrow. Bonding molecular orbital is upward arrow. So the two electrons we have to represent like this. And in sigma 1s, and here sigma star 1s, right? This sigma star 1s. This is called sigma star 1s. Sigma star is nothing but antibonding. In hydrogen molecule, there is no antibonding molecular orbital, and whereas it has only bonding molecular orbital. I hope it is clear. Next, continuation. Differences between bonding molecular orbital and antibonding. It is found by the constructive overlapping of atomic orbitals. First, we are discussing about bonding molecular orbitals. It is found by the constructive overlapping of atomic orbitals. And anti-bonding molecular orbitals, it is found by the destructive overlapping of atomic orbitals. Energy of bonding molecular orbital is lower than the atomic orbitals. Very important point. So the bonding molecular orbital is lower than the individual atomic orbitals. This means sigma 1s is less than s orbital. So atomic orbitals. Energy of antibonding molecular orbital is higher than the atomic orbitals. Means sigma star 1s is greater than s orbital. So that is energy of antibonding molecular orbital is higher than atomic orbitals. Next, electron density is higher between the nuclei, and electron density is minimum between the nuclei. Electrons in BMO favors chemical bonding. So bonding molecular orbital, they forms chemical bond, that is covalent bond. And anti-bonding molecular orbital do not favor chemical bonding. So may or may not contain a node. So as they have formed wave nature, they have a node as well as anti-nodal region. So has at least one nodal region. May or may contain a node. Next, conditions for the combination of atomic orbitals. The combining atomic orbitals must have same energy or comparable energy. So 1s orbital can combine 1s orbital only, but not with 2s orbital or 2s orbital with of higher energy. This is very important. So the combining orbital should have symmetry about the molecular axis. Among three axes, z-axis is conventionally taken as the molecular axis. Hence, 2pz orbital of an atom can combine with 2pz orbital of another atom, but not with 2px or 2py orbital. So even they are particular about x and y orbitals also. Next, the combining orbital should have should have maximum overlap. As the extent of overlapping increases, the electron density between the nuclei also increases. These are all the conditions for the combination of atomic orbitals. Now, before ending this session, I'll tell you one important formula. I'm taking a new slide. How to find hybridization. So to find hybridization, because in this we discussed about types of hybridization. To find hybridization, H is equal to half into B plus M minus C plus A. B plus M minus C plus A, capital A. So what is V? V is number of valence electrons on the central atom. V is called what? Number of atoms, number of valence electrons on the central atom. Number of valence electrons on the central atom. M is called number of monovalent atoms. Number of monovalent atoms attached to central atom. Monovalent, very important. And C is called cations and A is called anions. With this formula, we can find hybridization ions also. Number of cations, A is called number of anions. So for example, let us see hybridization in SO4 2 minus. To find hybridization in SO4 2 minus substance. SO4 2 minus. So using the formula, H is equal to half into B plus M minus C plus A. We can write H is equal to hybridization in SO4 2 minus is equal to 1 by 2 into sulfur has how many valence electrons? 6 valence electrons, sulfur. So 6 minus, sorry, 6 plus. There is no monovalent because oxygen is divalent. Oxygen is divalent. So 0, 6 plus 0 minus no cation because there is no positive charge. So minus 0. How many anions we have? 2 anions. So plus 2. So 6 plus 2, 8 by 2. This is equal to 4. 4 means sp3 hybridization. So in this way, this formula is important for this only. We can find hybridization in ionic species also. That is radical ions. Next, in this topic, we are discussed about hybridization. Two more hybridization we didn't discuss. That is DsP2 hybridization. DsP2. This type of hybridization usually given by transition metal compounds. Transition metals because they have 3D orbital. Transition metal compounds. DsP2 hybridization. And one more hybridation is sp3d3. sp3d3. sp3d3 means here one s orbital overlaps with 3p and 3d. 1s plus 3p plus 3d, resulting in the formation of seven new hybrid orbitals. 7 new hybrid orbitals. So example is IF7. IF7 sp3 hybridation. Example IF7. IF7, that is iodine hexafluoride, sorry, heptafluoride, iodine heptafluoride. So in this session we have discussed about hybridation mainly, and more about hybridation already we discussed, but here we discuss is introduction about molecular orbital theory, and more about molecular orbital theory we'll discuss in this session. And from this session we'll get questions from hybridation, the shape and the type of hybridation, very very important. So which are the following contains sp3 hybridation? They'll give 4 examples: sp2 hybridation, sp hybridation. And how to find sp, sp2, sp3 hybridation, already I told you. So one more method I will tell you, one more method for getting hybridation by taking whiteboard I'm giving now again. So this hybridation method for finding with ions also. One more method. So here to find hybridation, if we have to find n factor, alternative hybridation method. Alternative method for hybridation. To find hybridation. So by finding n factor, what is n? N factor, small n. By finding n factor, where n is equal to, so if n is equal to 2, it starts with 2 only, there is no values of n is equal to 2. If n is equal to 2, sp hybridation, n is equal to 3, sp2 hybridation, n is equal to 4, sp3 hybridation, n is equal to 5, sp3d hybridation, and n is equal to 4 can be sp3d or dsp2 also. dsp2 in case of transition metal is involved as central atom. If transition metal is involved as central atom, then it undergoes dsp2 hybridation, not sp3 hybridation. N is equal to 6, sp3d2, and n is equal to 7, sp3d3. So how to find n factor? Just by adding bond pairs and lone pairs. If any lone pairs is there, we have to add. So where n is equal to sum of bond pairs and lone pairs. Sum of bond pairs and lone pairs in a molecule. And the lone pairs in a molecule. Let us take an example now. Sulfur dioxide. How to calculate hybridation of sulfur dioxide? So sulfur dioxide. Sulfur has how many valence electrons? 6 valence electrons. Sulfur has 6 valence electrons. Sulfur has 6 valence electrons. So it has 6 sulfur. 1, 2, 3, 4, 5, 6. Now with two oxygens, it will combine two electrons because of double bond. So two oxygens. So one oxygen will share two electrons. So here how many bond pairs? 2 bond pairs. So here this is 1 bond pair, 2 bond pairs, and 1 lone pair. So total n is equal to 3. So it has these two pairs also will be taken as 1 pair. So we'll call it as 1 bond pair. Even though they are sharing 4 electrons, this is also bond pair. So 1 bond pair. So it has 2 bond pairs plus 1 lone pair. So total it is n is equal to 3. If n is equal to 3, what is the type of hybridation? sp2. I hope it is clear. If sp2 hybridation, actually if there is no lone pairs, the shape should be trigonal planar. But here, due to one presence of one lone pair, it has bent shape. It has what shape? bent shape because of presence of lone pairs. Similarly, we can find hybridization by using n factor. So for example, let us consider second example. This is first example. Now second example. Second example, xenon tetrafluoride, XeF4. Xenon, XeF4. So already we know xenon has how many valence electrons? 8 valence electrons because it is inert gas. 8 valence. 1, 2, 3, 4, 5, 6, 7, 8. So it combines with 4 fluorines. How many fluorines? 4. So 4 electrons. So and each fluorine will contribute only 1 electron. So it is 1 fluorine, 2 fluorine, 3 fluorines, and 4 fluorines. So here I am writing fluorine. The one which is shared by fluorine, it is indicated by cross mark. So it has how many bond pairs? 1, 2, 3, 4. 4 bond pairs. And how many lone pairs? This is one lone pair and this is another lone pair. So it has 2 lone pairs, 4 bond pairs and 2 lone pairs. On the whole, it is getting 6. 6 means sp3d2. So xenon tetrafluoride undergoes sp3d2. But shape is not pentagonal bipyramidal, sorry, octahedral. Its shape is different, Caesar shape. So sp3d2 hybridization, but shape is not octahedral like SF6. Actually, SF6 means octahedral, but here it is not octahedral because of the presence of lone pairs, 2 lone pairs. I hope it is clear. So in this way, 2 alternate methods we are going to find hybridization. So next, we are going to discuss more about MOT in the next session. Thank you all.